Imagine standing on a cliff at night and looking up at the sky. The stars you see are so far away that the light reaching your eyes has been traveling for years, decades, even millennia. Every tiny point of light is not simply a glowing speck but a vast sun like our own, separated from us by distances that words can barely capture. To even begin to understand the scale of the universe, we must start with the strange language of light itself. Light moves faster than anything else in nature, a cosmic speed limit that nothing can exceed. At almost 300,000 kilometers per second, light could circle the entire planet Earth more than 7 times in a single second. Yet even this unbelievable speed struggles to conquer the universe's expanse. Astronomers measure cosmic distances not in kilometers, but in light years. The distance that light covers in one full year, that is almost 10 trillion kilometers. A number so vast that it strains the imagination. When we say a star is 10 light years away, we are really saying that the light you see tonight left that star 10 years ago, long before today's events on Earth unfolded. If a star is 1,000 light years away, then its light began its journey during the age of medieval castles and ancient dynasties. Distance in space is also measured in parsecs, short for parallax arc seconds. A parsec equals about 3 1/4 light years, a unit born from geometry as astronomers compared tiny shifts in starlight positions against the background of the sky. Each of these terms, light year and parsec, is a human attempt to wrestle with an immensity that dwarfs our daily experience. If we keep going outward, the scales balloon to staggering levels. The Milky Way galaxy itself is about 100,000 light years across, a collection of hundreds of billions of stars bound in a rotating spiral. Even so, the Milky Way is but one galaxy among a sea of others. The observable universe, the part we can in principle detect, stretches for a radius of about 46 billion light years in every direction. This does not mean the universe is only that size, but rather that the expansion of space has carried galaxies away faster than their light can ever reach us. Light that has traveled for nearly the entire age of the cosmos has finally arrived. And beyond that horizon lies an unreachable forever. Here we find one of the most important truths of physics. Nothing can move faster than light through space, but space itself can expand. Galaxies are not racing like rockets through a fixed void. Instead, the very fabric of the universe is stretching, pulling them away from one another. Over time, this expansion means that more and more galaxies drift beyond our sight, their light stretched into invisibility. The speed of light remains absolute, but the stretching of space is like a conveyor belt, moving everything farther apart. This is why we can only speak of the observable universe. There may be much more beyond that, perhaps infinite, but it is forever hidden behind this cosmic curtain. When we put all of this together, our minds face a scale of both distance and time that is almost crushing. Every glance at the stars is a kind of time travel. Looking at the Andromeda galaxy, more than 2 million light years away, means seeing it as it was when early human ancestors first shaped stone tools. Looking at distant quasars, billions of light years away, means witnessing galaxies as they were when the universe itself was young. We never see the cosmos as it is, only as it was. The farther we look, the older the light. The more powerful our telescopes, the deeper into history we peer. This is the illusion of emptiness. What seems like black space between stars is not empty at all. It is filled with invisible matter, faint light, and the constant hum of expansion. The distances are so great that the gaps overwhelm us. But in truth, every region of the universe is a part of this interconnected web. From the smallest spark of light to the grandest void, the scale of the cosmos reshapes how we see our place. Once we understand the immensity of space, the next question naturally arises. What fills it? What are the engines that light the darkness, the forges that create the very atoms of our bodies? To answer that, we must turn from the vast emptiness to the blazing furnaces that keep the night sky alive. And so, having measured the distances, we now begin to populate them with wonders. The farther we travel into the thought experiment of cosmic distances, the more our everyday sense of scale begins to unravel. Consider the nearest star system beyond the Sun, Alpha Centauri. It lies just over 4 light years away. In earthly terms, that is about 40 trillion kilometers, a journey so immense that even the fastest spacecraft humanity has ever built would take tens of thousands of years to arrive. And Alpha Centauri is simply our closest neighbor. The rest of the galaxy stretches outward in a vast spiral so wide that light itself needs 100,000 years to cross it. Our imaginations bend under numbers so large. Yet these are only the first steps across a universe without edges. Picture leaving the Milky Way entirely. Beyond its stars lies the local group, a small cluster of galaxies bound together by gravity. Within this group, the Andromeda Galaxy looms largest, a spiral even bigger than our own, set on a slow-motion collision course with us. Though it feels apocalyptic to imagine two galaxies colliding, the truth is stranger. The stars themselves are so far apart that when galaxies merge, most stars glide past one another without ever touching. Collisions are not cataclysms of fire but dances of gravity, where spirals twist into ellipses and cosmic tides weave new patterns of starlight. Yet even the local group is only a small part of a still larger family called the Virgo supercluster, which in turn is only one thread in the vast cosmic web. As scientists chart these distances, they rely on light not just as a measure but as a messenger. When a supernova explodes in a galaxy hundreds of millions of light years away, we see it only when its light finally completes the journey across unimaginable gulfs. The explosion itself happened long before humans even existed. The universe is a time machine, and every photon is a story carried across the ages. This is why astronomers build ever more sensitive telescopes. They are not only looking farther, they are listening deeper into the past, hoping to hear whispers from the first stars that ever shone. The scale is so vast that even the speed of light, so absolute, begins to feel slow. If you could ride a beam of light leaving Earth tonight, it would take you 8 minutes to reach the Sun, a little over 1 hour to reach Jupiter, and 4 hours to reach Neptune at the outer edge of the planetary system. But to escape the solar system entirely and reach the nearest stars, you would still need years upon years. The interstellar gulf is not like crossing a desert or an ocean. It is an emptiness where distance itself becomes a barrier stronger than any wall of stone or steel. Yet the expansion of space introduces another twist. Distant galaxies are not merely far away, they are receding from us. The farther a galaxy lies, the faster it moves away, a discovery first made by Edwin Hubble in the early 20th century. This cosmic expansion means that light from galaxies billions of light years away is stretched as it travels, shifting into the red part of the spectrum. Astronomers call this redshift, and it is one of the great clues that revealed the universe itself is growing. Even though nothing can travel through space faster than light, space itself can grow so quickly that galaxies seem to flee from us faster than light can catch them. Beyond a certain horizon, their signals fade, swallowed into the infinite night. The observable universe, therefore, has a boundary not defined by walls but by time. We can see only as far as light has had time to travel since the beginning. That limit is about 46 billion light-years in radius. Anything beyond remains invisible, though it still exists. In fact, the true universe might be vastly larger, perhaps infinite. We are like sailors on an endless ocean, seeing only to the horizon, yet knowing that waters stretch far beyond. This horizon is not just a poetic idea, but a hard fact. It marks the edge of what any telescope, present or future, can ever reveal. And so we find ourselves caught between scales that shrink and expand in ways almost impossible to hold in the mind. From the solar system, to the galaxy, to the cosmic web, each step multiplies distances until even light seems inadequate. Yet, these scales are not only abstract numbers, they are real distances shaping real stories. They determine how galaxies evolve, how stars live and die, and how humans can dream of exploring worlds far beyond our own. Every step outward reveals more, but also more questions. If the universe is this vast, what fills it? What powers illuminate its immensity? The answer awaits in the stars themselves, those radiant furnaces scattered like jewels across the infinite dark. The vastness of the universe is not only measured in distance but in time. When we speak of light years, we are speaking of history itself. The light that falls on Earth tonight may have begun its journey before humanity learned to write, before life itself crawled from the sea. To gaze into the cosmos is to look back through epochs older than mountains, older than oceans, older than our planet itself. The beginning of this story lies nearly 14 billion years ago, when the universe was born in the event we call the Big Bang. From that moment, space has been expanding, carrying galaxies apart as if embedded in an inflating fabric. This expansion is not like an explosion scattering debris into emptiness. It is the stretching of space itself, a silent growth that continues even now. This truth leads to an even stranger realization. The most distant galaxies we see today are not where they appear to be. By the time their light reaches us, they have drifted billions of light years farther away. The observable universe is therefore not a snapshot of the present, but a ghostly record of how things once were. Astronomers often speak of a light cone, a boundary defined by the paths that light has taken to reach us. We live inside this cone, surrounded by ancient messages arriving from every direction. The cosmic microwave background, a faint afterglow that fills all of space, is the oldest message of all. Light released when the universe was only a few 100,000 years old. It is the fossil radiation of creation itself, stretched by billions of years of expansion until it now hums as microwaves. When we measure these scales, our mathematics reaches into realms that feel almost absurd. The diameter of the observable universe is about 92 billion light-years, which means that even light, traveling at 300,000 kilometers per second, would need 92 billion years to cross it. Yet the universe itself is only 14 billion years old. How can that be? The answer lies again in expansion. While the light was on its journey, the fabric of space grew, stretching the distance far beyond what light could traverse in the same time. This is the paradox of cosmic scale, where time and space interweave into shapes that challenge our most basic intuitions. For us, beings of limited lifespan, these numbers may seem irrelevant, yet they shape everything we know. The fact that the speed of light is finite means that the universe has a built-in delay. We can never see the present moment beyond our own world. We can only ever see the past, recorded in photons. Even the sun is delayed, its light taking 8 minutes to reach us. If it vanished right now, we would not know until those 8 minutes had passed. The stars are even greater delays. To see the Andromeda galaxy is to look back more than 2 million years. To see the faintest galaxies detected by the James Webb Telescope is to look back more than 13 billion years, to a time when the first stars were igniting in a cosmos still shrouded in primordial darkness. The scale of the universe is humbling, yet it also invites wonder. It means that every night sky is a living museum of time. The darkness is not empty. It is full of messages arriving at this very instant from every corner of the cosmos. Each star is a story, each galaxy a chapter, each faint glow a relic of creation. To stand beneath the stars is to stand at the crossroads of infinity and eternity. A creature of fleeting years, gazing across billions, and so the illusion of emptiness gives way to revelation. Space is vast beyond reckoning, but it is not void. It is filled with light, with memory, with the echoes of creation itself. Once we understand this, we are ready to go deeper. Now that we have traced the scale of the cosmos, we must begin to fill it with its true inhabitants. The next part of our journey turns to the stars themselves, those blazing forges of matter and energy that not only light the universe, but create the very atoms of which we are made. The distances have prepared us. The immensity has humbled us. Now it is time to see what burns within the dark. The night sky is not silent. Every point of light is a sun, each one a raging furnace, each one writing a story of birth, life, and death. Our own sun is but an average star, steady and middle-aged, glowing with quiet power. Yet, across the cosmos, stars come in endless variety, from the faint glow of red dwarfs that burn slowly for trillions of years, to the blazing hypergiants that live fast and die young, expelling their innards into the universe in spectacular detonations. To understand the cosmos, we must understand stars, for they are the forges of creation, the engines that shape galaxies, the makers of every atom in our bodies. Stars are born from clouds of gas and dust. Within vast nebulae, gravity gathers matter, pulling atoms together until their pressure becomes overwhelming. When the core of this gathering cloud grows hot enough, nuclear fusion begins. Hydrogen, the simplest element, is fused into helium, releasing energy with every transformation. That energy pushes outward as light and heat, balancing the crushing pull of gravity. The star is born in this delicate truce, its light pouring into the void. For most of its life, a star maintains this balance, burning steadily in what astronomers call the main sequence. Our sun has shone in this way for about 4.5 billion years, and it will continue for several billion more. But stars are not eternal. Their fate is written in their mass. Small stars, like red dwarfs, sip their fuel so slowly that they may outlive the universe itself, shining faintly for trillions of years. Medium stars, like the sun, swell into red giants near the end of their lives. In time, the outer layers drift away into space, leaving behind a small, dense core called a white dwarf. These glowing embers fade slowly, cooling into darkness over unimaginable spans. Larger stars, however, walk a far more violent path. They burn their fuel at a furious rate, racing through their lives in only millions of years. When their fuel is exhausted, their cores collapse under the weight of their own gravity, triggering explosions so bright they can outshine entire galaxies. These are supernovae, among the most powerful events in nature. A supernova is not only a death but a creation. In the searing heat and pressure of the blast, atoms are crushed together to form new elements. Gold, silver, uranium, all the heavy atoms that make up planets and people, are forged in these stellar deaths. Every ring on a finger, every coin in a pocket, every molecule of iron in your blood was once inside the heart of a star that lived and died long before the sun was born. To say that we are stardust is not poetry, it is a fact of physics, written in the atoms themselves. Without the death of ancient suns, there would be no life, no planets, no oceans, no human beings to look up and wonder. Stars also shape the galaxies they inhabit. Their light sweeps away clouds of gas, their winds carve vast cavities, their deaths enrich the cosmos with new matter. The rhythm of star birth and death is the heartbeat of galaxies, recycling matter again and again into new generations of suns and worlds. If galaxies are islands in the dark sea of space, then stars are the cities, burning with life, glowing with stories untold. And yet, for all their power, stars remain bound by the same cosmic laws. They are born, they live, and they die. Their brilliance may last for millions or billions of years, but the end always comes. In that end lies both destruction and creation, for the universe wastes nothing. Even in death, stars give back to the cosmos, seeding it with the elements of new beginnings. This is the legacy of stars. They are the great alchemists of the universe, turning simple hydrogen into the richness of the periodic table. They are the storytellers of time, burning brightly and fading, each one a chapter in the grand chronicle of creation. To understand stars is to understand ourselves, for without them, we would not exist. And yet, among these forges of light are monsters stranger still, objects so extreme that they defy even the imagination. To meet them, we must look into the abyss, where gravity reigns supreme, and not even light can escape. Stars are storytellers written in fire, and their tales unfold differently depending on their size. The smallest among them, red dwarfs, are the quiet keepers of eternity. They burn their hydrogen so sparingly that their lives stretch into trillions of years, far longer than the universe has yet existed. If we look far into the cosmic future, when most suns like ours have long since died, it will be the faint red dwarfs that remain, glowing softly in the endless night. Some of these ancient embers may still be shining when everything else is gone. By contrast, the largest stars live fast and furious. Blue giants and hypergiants shine with searing intensity, some burning more brightly than 1,000,000 suns combined. But that brilliance comes at a price. Their fuel is devoured in only a few million years, a blink of an eye compared to the lifespan of the cosmos. These stars often end their lives in cataclysms so violent that entire galaxies can witness their passing. In those moments, the universe reveals both its most terrifying power and its most generous gift, scattering new elements across space. Among the remnants of such stellar violence are neutron stars, objects so dense that a teaspoon of their matter would weigh more than a mountain. Born when a massive star collapses, They are tiny, no larger than a city, yet containing more mass than the Sun. Some spin with incredible speed, sending out beams of radiation like cosmic lighthouses. These are pulsars, their signals sweeping across the universe with perfect regularity. Astronomers first detected them in the 1960s, and for a moment, their precision seemed so uncanny that they were nicknamed Little Green Men, as if perhaps aliens were calling. But the truth was stranger. They were the voices of collapsed stars, still speaking in the language of physics long after their fiery deaths. Other stars collapse into black holes, the ultimate traps of the universe. Unlike neutron stars, which resist gravity with the pressure of neutrons themselves, black holes collapse completely, leaving behind a region where gravity is so intense that nothing, not even light, can escape. To fall into such an object is to vanish from the universe, erased from view, though the mass remains, bending space and time around it. Some of these black holes are only a few times more massive than the Sun, while others, millions or billions of times greater, sit at the centers of galaxies. These supermassive black holes shape the fates of galaxies, anchoring their stars and sometimes unleashing jets of energy that stretch for thousands of light years. But black holes are not the only extremes born from stellar death. Sometimes, a star dies not with a collapse, but with a whisper. Our own Sun will follow this quieter path. In about 5 billion years, it will swell into a red giant, its outer layers expanding until they engulf Mercury and Venus, and perhaps even Earth. Eventually, the Sun will shed its outer layers, creating a glowing shell of gas known as a planetary nebula. At its center will remain a white dwarf, a stellar ember, no larger than Earth, but with a mass close to that of the Sun. Over trillions of years, it will cool, fading slowly into darkness. This is the destiny of stars like ours, quiet and gentle, compared to the explosive fates of giants. Through these endings, the cosmos recycles itself. The carbon in our cells, the calcium in our bones, the oxygen we breathe, all were forged in stars and scattered across space in their deaths. When new stars form, they inherit this material, building planets, oceans, and eventually life. In this way, every breath we take is part of a cycle that began in stars long gone. We are connected to them not by metaphor but by the atoms that shape us. And yet, for all the brilliance of stars, for all the beauty of their births and deaths, there are darker corners of the universe where even starlight cannot reach. There, gravity rules with absolute power, and mysteries still defy our understanding. To follow the story of stars to its ultimate extreme, we must step across the event horizon and face the deepest abysses of the cosmos. The lives of stars are not merely stories of light, but of transformation. Some stars end in quiet, others in fury, and a rare few end in ways so extreme that even astronomers hesitate to imagine them. Among the most violent are the pair instability supernovae, explosions so vast that they do not leave behind a neutron star or a black hole at all. Instead, the entire star is obliterated in a single detonation, scattering its mass across the cosmos. These events occur when the cores of extraordinarily massive stars become unstable, their energy turning into pairs of matter and antimatter particles that destabilize the delicate balance holding them together. What follows is not survival, but total annihilation. A cosmic firework that leaves nothing behind. Another class of stellar remnant is the magnetar, a kind of neutron star endowed with magnetic fields so strong that they defy human comprehension. A magnetar's field can be 1,000 trillion times more powerful than the Earth's magnetic field. If one were as close as the Moon, its magnetic pull could erase every credit card on Earth and twist the very atoms in our bodies. Though these monsters are rare, their flares can outshine an entire galaxy for brief moments, sending pulses of energy racing through the universe. To detect them is to be reminded that even in death, stars can roar with incredible force. The diversity of stellar fates is a map of cosmic creativity. Stars are not all alike, and the galaxies are richer for it. Small stars nurture stability, glowing faintly for eons, while giant stars paint the heavens with sudden violence. Between them lies a continuum of possibilities, each dictated by the unyielding laws of physics, each contributing to the cosmic cycle of birth and rebirth. No star truly disappears without leaving a legacy. Even the quiet embers of white dwarfs enrich the interstellar medium with matter and energy. Every generation of stars lays the foundation for the next, in a chain that has continued since the universe's earliest epochs. Consider this truth. When the first stars ignited, the universe contained only hydrogen and helium, the simplest elements. Those primordial giants lived short lives, producing heavier elements in their cores and seeding them into the young cosmos through titanic explosions. The second generation of stars carried these elements forward, creating still more. By the time the sun was born, the universe had been enriched with carbon, oxygen, silicon, and iron, materials that would become planets, oceans, mountains, and life. We are heirs to a process billions of years old, the result of countless stellar lives and deaths. Every star that shines today is part of that unbroken chain. It is this continuity that gives stars their greatest meaning. They are more than points of light scattered in the night sky. They are engines of creation, keepers of time, and ancestors of life. Their fiery cores sculpt the periodic table. Their deaths shape the galaxies. Their remnants remind us of the raw power of physics. And through all of it, they invite us to look upward and wonder. For in their glow, we see not just the cosmos as it is, but the story of how it came to be, and perhaps even a glimpse of how it will continue long after humanity is gone. As we end this chapter, we stand at a threshold. Stars have shown us creation and destruction, brilliance and silence, fury and stillness. Yet there exists a frontier where their story is taken to its ultimate extreme, where matter itself collapses beyond recognition, where gravity becomes so fierce that time and space themselves are twisted. Beyond the lives and deaths of stars lies the abyss of black holes, the traps of the universe from which no light escapes. To continue our journey, we must step closer to the darkness and see what waits within. There are places in the universe where the rules we know no longer apply, where gravity becomes so fierce that not even light can escape. These are black holes, the ultimate ends of certain stars, and perhaps the most mysterious objects in all of science. To approach them is to approach a paradox, for they are at once invisible and yet profoundly influential. Though they emit no light, their presence shapes galaxies, bends space, and alters time itself. They are the universe's traps, silent abysses that challenge our very understanding of reality. A black hole begins as a star, but not an ordinary one. Only the most massive stars can take this path. When such a giant exhausts its fuel, its core can no longer resist the inward pull of gravity. For smaller stars, collapse halts at the stage of a white dwarf or a neutron star, supported by the pressures of atoms or neutrons. But for the most massive stars, no force is strong enough to withstand the crushing weight. Gravity wins, and the core collapses completely, compressing matter into a point of infinite density, what scientists call a singularity. Around this singularity forms the event horizon, a boundary beyond which nothing, not even light, can return. The star is gone, replaced by a region of space where physics itself seems to break. If you were to approach a black hole, the experience would defy imagination. From far away, the black hole would appear as a dark sphere, silhouetted against the glow of stars, its presence marked by the light it swallows and the matter it consumes. As you drew closer, you would see space itself distorted, light bending into arcs and spirals, stars smeared across the sky. If you crossed the event horizon, no signal could ever reach the outside world. To those who remain outside, your fall would appear to slow, time stretching until you seemed frozen on the edge. But to you, time would continue, and the descent would be swift. In the final moments, as you neared the singularity, tidal forces would tear you apart, stretching your body into a thin strand, in a process scientists call spaghettification. It is a fate as strange as it is final. Despite their terrifying nature, black holes are not rare. Our own galaxy is home to millions of them, remnants of stars that lived and died over billions of years. The most massive of them lie at the heart of galaxies, where they have grown to monstrous proportions. These supermassive black holes contain millions or billions of solar masses, anchoring their galaxies and sometimes powering quasars, the brightest beacons in the cosmos. They are the silent giants of the universe, their gravity binding entire systems of stars. Without them, galaxies might not exist in their present form. Yet, for all we know, mysteries remain. What truly happens at the singularity, where our mathematics falters? Does information swallowed by a black hole vanish forever, or is it somehow preserved in ways we do not yet understand? These are not idle questions, but deep puzzles that touch the very foundations of physics. Black holes are not simply astrophysical objects. They are laboratories of extremes, where gravity, quantum mechanics, and relativity collide. To understand them is to inch closer to a theory of everything. A single framework that unites the laws of the very large and the very small. They are, in every sense, the edge of knowledge. They mark the places where science itself must stretch, where imagination and mathematics are forced to go hand in hand. And though they are dark, they illuminate by their mystery, showing us the limits of what we know and pointing toward the discoveries still to come. But the story of black holes does not end with fear, for in their silence, they also sing. The supermassive black hole at the center of our galaxy, Sagittarius A star, emits radio waves that astronomers sometimes describe as a kind of purring. These invisible vibrations remind us that even the most forbidding objects in the cosmos are not beyond reach. With telescopes and patient study, we can listen to their voices, chart their shadows, and begin to understand the strange beauty of their nature. Black holes are not always quiet. In fact, some of the brightest objects in the universe owe their brilliance to the darkness of these gravitational traps. When gas and dust spiral toward a black hole, they form what is called an accretion disk, a whirlpool of matter heated to incredible temperatures as it falls inward. Friction and compression transform this gas into a blazing beacon, releasing more energy than entire galaxies of stars. To an observer, it is a paradox. These phenomena are known as quasars, and they are among the most powerful sources of radiation in the cosmos. Quasars reveal the influence of supermassive black holes at the hearts of galaxies. These giants, containing millions or even billions of times the mass of the Sun, shape the evolution of their host galaxies. Their gravity keeps stars in orbit, their jets of energy regulate the birth of new stars, and their activity can determine the fate of entire clusters. Without these hidden anchors, galaxies might be chaotic, their stars drifting apart into the void. Instead, black holes serve as unseen architects, holding galaxies together with their silent weight. The black hole at the center of our own Milky Way, called Sagittarius A star, is a supermassive black hole about 4 million times the mass of the Sun. Though dormant compared to the raging quasars of the distant universe, it still exerts immense influence. Stars whirl around it at breathtaking speeds, some completing their orbits in only a handful of years, despite distances that would dwarf our solar system. Watching these stars trace their paths provides one of the most direct proofs that black holes are real. Their dance is a silent testimony to the presence of an invisible giant. Black holes also reveal themselves through gravitational waves, ripples in the fabric of space and time predicted by Einstein's theory of relativity and confirmed a century later by sensitive detectors on Earth. When two black holes spiral together and merge, the collision sends out waves that travel across the universe, carrying with them the signature of the cataclysm. In 2015, scientists recorded such a signal for the first time, opening a new way of observing the cosmos. These waves allow us to hear the universe, to detect events that light cannot reveal, and to measure the properties of black holes directly. Despite all of this, black holes remain enigmatic. They are defined not by what they are, but by what they hide. The event horizon is not a surface in any ordinary sense, but a boundary in space-time. Beyond it, all paths lead inward, all futures converge on the singularity. What happens there is a question that pushes the limits of physics. Some theories suggest that information falling into a black hole is lost forever, while others argue it must be preserved in some hidden way. This debate touches the core of quantum mechanics, relativity, and the nature of reality itself. Black holes are not simply destinations of matter, they are crucibles for our understanding of the universe. As we continue to study them, we find that they are not merely exotic rarities, but central to the structure of the cosmos. Every large galaxy harbors a supermassive black hole at its heart. Their growth and activity may be linked to the formation of galaxies themselves. The universe we see, filled with stars and clusters, may owe its shape in part to these silent engines. Far from being isolated oddities, black holes may be essential to the very architecture of creation. And so, the image of black holes begins to shift. They are not only destroyers but also shapers, not only traps but also beacons, not only mysteries but also tools for discovery. By studying them, we learn about gravity, time, matter, and energy at their most extreme. They are windows into realms of physics otherwise unreachable. Each observation, whether a star whipping around Sagittarius A star, a quasar blazing across the deep universe, or a ripple in space-time captured on Earth, brings us closer to understanding the ultimate limits of nature. Yet the story of extremes does not end in darkness. Beyond the black holes, there are phenomena of staggering brightness, galaxies themselves, vast collections of stars, and matter that stretch across unimaginable distances. Where black holes consume, galaxies create, shaping the heavens with light. To move forward in our journey, we must leave behind the abyss and turn toward the shining islands that fill the cosmic ocean. Black holes are not always quiet. In fact, some of the brightest objects in the universe owe their brilliance to the darkness of these gravitational traps. When gas and dust spiral toward a black hole, they form what is called an accretion disk, a whirlpool of matter heated to incredible temperatures as it falls inward. Friction and compression transform this gas into a blazing beacon, releasing more energy than entire galaxies of stars. To an observer, it is a paradox. A dark hole, framed by light so bright that it can be seen across billions of light years. These phenomena are known as quasars, and they are among the most powerful sources of radiation in the cosmos. Quasars reveal the influence of supermassive black holes at the hearts of galaxies. These giants, containing millions or even billions of times the mass of the Sun, shape the evolution of their host galaxies. Their gravity keeps stars in orbit, their jets of energy regulate the birth of new stars, and their activity can determine the fate of entire clusters. Without these hidden anchors, galaxies might be chaotic, their stars drifting apart into the void. Instead, black holes serve as unseen architects, holding galaxies together with their silent weight. The black hole at the center of our own Milky Way, called Sagittarius A star, is a supermassive black hole about 4 million times the mass of the Sun. Though dormant compared to the raging quasars of the distant universe, it still exerts immense influence. Stars whirl around it at breathtaking speeds, some completing their orbits in only a handful of years, despite distances that would dwarf our solar system. Watching these stars trace their paths provides one of the most direct proofs that black holes are real. Their dance is a silent testimony to the presence of an invisible giant. Black holes also reveal themselves through gravitational waves, ripples in the fabric of space and time, predicted by Einstein's theory of relativity and confirmed a century later by sensitive detectors on Earth. When two black holes spiral together and merge, the collision sends out waves that travel across the universe, carrying with them the signature of the cataclysm. In 2015, scientists recorded such a signal for the first time, opening a new way of observing the cosmos. These waves allow us to hear the universe, to detect events that light cannot reveal, and to measure the properties of black holes directly. Despite all of this, black holes remain enigmatic. They are defined not by what they are, but by what they hide. The event horizon is not a surface in any ordinary sense, but a boundary in space-time. Beyond it, all paths lead inward, all futures converge on the singularity. What happens there is a question that pushes the limits of physics. Some theories suggest that information falling into a black hole is lost forever, while others argue it must be preserved in some hidden way. This debate touches the core of quantum mechanics, relativity, and the nature of reality itself. Black holes are not simply destinations of matter, they are crucibles for our understanding of the universe. As we continue to study them, we find that they are not merely exotic rarities, but central to the structure of the cosmos. Every large galaxy harbors a supermassive black hole at its heart. Their growth and activity may be linked to the formation of galaxies themselves. The universe we see, filled with stars and clusters, may owe its shape in part to these silent engines. Far from being isolated oddities, black holes may be essential to the very architecture of creation. And so, the image of black holes begins to shift. They are not only destroyers but also shapers, not only traps but also beacons, not only mysteries but also tools for discovery. By studying them, we learn about gravity, time, matter, and energy at their most extreme. They are windows into realms of physics otherwise unreachable. Each observation, whether a star whipping around Sagittarius A star, a quasar blazing across the deep universe, or a ripple in space-time captured on Earth, brings us closer to understanding the ultimate limits of nature. Yet the story of extremes does not end in darkness. Beyond the black holes, there are phenomena of staggering brightness, galaxies themselves, vast collections of stars and matter that stretch across unimaginable distances. Where black holes consume, galaxies create, shaping the heavens with light. To move forward in our journey, we must leave behind the abyss and turn toward the shining islands that fill the cosmic ocean. The extremes of black holes defy ordinary imagination. Some are small, just a few times more massive than the Sun, the remnants of stars that collapsed at the end of their lives. Others are so vast that they dwarf entire star systems, swallowing light and time on scales we can scarcely picture. These are the ultramassive black holes, titans with billions of solar masses. The largest ever detected may be more than 60 billion times the mass of the Sun, lurking at the center of a galaxy so distant that its light began traveling toward us when Earth was still young. Their event horizons could engulf the orbits of planets, stretching across distances comparable to entire solar systems. To stand near such a monster, if it were possible, would be to witness gravity itself made visible, a void so deep that nothing could resist its pull. And yet, black holes are not always silent. Some feed ravenously, devouring gas and stars unlucky enough to drift too close. As matter spirals inward, the black hole unleashes jets of energy that can blast across millions of light years. These cosmic lighthouses pierce the dark, marking the presence of something that cannot otherwise be seen. Entire galaxies can be reshaped by this violence. Star formation may be quenched as black holes heat and scatter the gas that would otherwise create new suns. In this way, they play the role of both destroyer and regulator, sculpting the life cycles of galaxies themselves. Even more mysterious are the questions black holes raise about the fate of information. Physics insists that information about the state of matter can never truly vanish. Yet when matter falls into a black hole, it seems to be erased from existence. This puzzle, known as the information paradox, has challenged the greatest scientific minds. Some believe the information is preserved in subtle patterns at the event horizon, while others suspect new physics may be required to resolve the conflict. The answer could reshape our understanding of quantum mechanics and space-time itself. Black holes do not simply swallow matter, they swallow certainty, forcing us to rethink the rules we thought unbreakable. For all their strangeness, we are no longer limited to imagining them. In 2019, the Event Horizon Telescope produced the first image of a black hole, capturing the glowing ring of matter around the giant in the galaxy Messier 87. The image was not a photograph in the ordinary sense, but a synthesis of data from telescopes across the world, combined to form a single planet-sized eye. What it revealed was astonishing. A shadow, cast not by an object but by the absence of escape, outlined in a halo of superheated light. It was proof made visible. A cosmic silhouette that confirmed Einstein's predictions and gave humanity its first direct glimpse into the abyss. And the discoveries continue. With instruments like the James Webb Telescope, astronomers are probing the earliest epochs of the universe, searching for the seeds of the first black holes. Some appear to have formed astonishingly quickly, raising questions about how such massive giants could grow so early in cosmic history. Were they born already massive from the collapse of enormous primordial clouds, or did they grow with unthinkable speed by feeding on their surroundings? The answer remains one of the most compelling mysteries of modern astronomy. The story of black holes, then, is not only about death, but about transformation, not only about endings, but about beginnings. They are the edge of physics, the keepers of secrets, the monsters, and the teachers of the universe. They show us that even in darkness, there is discovery. They remind us that limits are not barriers, but invitations to seek deeper truths. And they guide us, paradoxically, to light. For beyond these dark abysses lie the galaxies themselves, sprawling cities of stars, each one a theater where the drama of creation and destruction plays out on scales even greater than black holes alone. If black holes are the heartbeats, galaxies are the bodies, weaving billions of suns into graceful spirals, ovals, and clusters. To continue our journey, we must leave behind the silence of the abyss and enter the luminous realms of galaxies, the shining islands of the cosmos. When we lift our eyes to the night sky, the band of the Milky Way stretches above us, a river of light shimmering across the darkness. What we see as a hazy glow is in truth the combined radiance of billions of stars, all members of a vast spiral galaxy that is our home. Yet the Milky Way is but one among countless others. The universe is filled with galaxies, each a congregation of stars, planets, gas, and dust, bound together by gravity into shapes of astonishing beauty. They are the great islands of the cosmos, separated by gulfs so immense that light itself requires millions of years to cross from one to the next. The Milky Way is a barred spiral galaxy measuring about 100,000 light-years across. It contains several hundred billion stars, along with clouds of gas and dust from which new stars continue to be born. Our Sun lies on one of its spiral arms, far from the crowded core, orbiting the center once every 200 million years. Though vast, the Milky Way is not unique. Nearby lies the Andromeda Galaxy, a spiral even larger than our own. Across billions of years, these two giants are on a slow collision course. In about 4 billion years, they will merge into a single enormous galaxy, a cosmic dance that will transform the night sky. Stars will swirl into new patterns, long arcs of light stretching across the heavens, while supermassive black holes at the centers of each galaxy spiral together and merge in a final titanic event. Despite the grandeur of such collisions, the stars within rarely strike one another. They are far too widely spaced, like grains of sand scattered across a vast desert. Instead, the interaction reshapes the galaxies themselves, turning spirals into ellipses, igniting bursts of star formation as gas clouds crash together and collapse into new suns. Far from being destructive, galaxy collisions are engines of renewal, sculpting new forms from old, leaving behind galaxies of breathtaking beauty. Yet galaxies are as diverse as the stars they contain. Some, like our Milky Way and Andromeda, are spirals, graceful disks with sweeping arms. Others are ellipticals, massive and rounded, filled with old stars but little gas for new ones. Still others are irregular, chaotic in form, shaped by collisions and chance. Some are tiny dwarf galaxies with only a few million stars, while others are colossal giants. One of the largest known, IC1101, is estimated to be nearly 6 million light-years across, holding hundreds of trillions of stars. To imagine such a leviathan is to imagine a city of suns sprawling beyond comprehension. Galaxies also display remarkable anomalies. There are ring galaxies, formed by collisions that send ripples through the disk of a spiral, creating luminous circles of stars. There are lenticular galaxies, halfway between spirals and ellipticals, their arms faded into smooth, lens-like shapes. There are galaxies with double cores, galaxies with streams of stars stretching like ribbons into intergalactic space, and galaxies so faint that they can barely be seen, even with the most powerful telescopes. Each one is a unique expression of cosmic history, a record of the forces that shaped it. Astronomers once believed the Milky Way was the entire universe. Only in the 20th century did Edwin Hubble show that the faint smudges on the sky were not gas clouds but entire galaxies, each as vast as our own. This revelation transformed our view of the cosmos. Instead of a single island, the universe became an ocean, filled with billions upon billions of galaxies. Each one is a realm of possibilities, with its own stars, planets, and perhaps life. In the grand scale, galaxies form structures of their own, clustering into groups and superclusters, weaving into filaments that span billions of light-years. But even before we step into that greater web, the galaxies themselves are enough to stir wonder. They are not only magnificent in form, but fundamental to the story of the universe. Without galaxies, there would be no stars, no planets, no life. They are the stage upon which the drama of creation unfolds, the islands that give shape to the cosmic sea. And so, As we sail between these luminous realms, we see not emptiness but abundance, not loneliness but countless companions in the dark. The galaxies remind us that the universe is not a barren void but a thriving cosmos, filled with beauty and possibility. To journey among them is to glimpse the architecture of infinity itself. The deeper we look into the universe, the more galaxies we find, each with its own character, each telling a different tale. Some galaxies glow with youthful light, their arms bright with newborn stars, while others are ancient and weary, their brilliance faded as their stellar nurseries have gone cold. Spirals, with their elegant arms, are often places of renewal. Gas and dust swirl through them, feeding the birth of stars that shine blue and hot. Elliptical galaxies, by contrast, are often graveyards, filled with older, redder stars, their supplies of gas long since exhausted. They glow softly, vast and stately, but their days of creation are largely behind them. Between these two extremes are the lenticular galaxies. Suspended in a kind of cosmic twilight, they retain the disk shape of spirals, but lack the active arms. Their stars are older, their gas depleted, their evolution shaped by past interactions or slow processes of exhaustion. Many appear to be spirals transformed by the environment, stripped of their raw material by gravitational tides or by encounters with other galaxies. They stand as reminders that galaxies are not static, but evolve over time, reshaped by forces both within and without. And then there are the oddities, galaxies that defy neat classification. Ring galaxies, rare and spectacular, form when a smaller galaxy plunges through the disk of a larger one. The collision sends out waves like ripples on a pond, compressing gas into circles where stars ignite in bursts of brilliance. Some galaxies are warped, their shapes twisted by unseen companions. Others stretch long streams of stars into space, tidal tales that mark the violence of past encounters. Some seem almost ghostly, with light so faint that they appear only as whispers against the background sky. Our own Milky Way is far from solitary. It is surrounded by dozens of dwarf galaxies, faint companions that orbit like satellites around a giant. These small galaxies are fragile, their stars often stripped away by the Milky Way's gravity, leaving behind streams of light that arc across the sky. Similar relationships exist throughout the cosmos. Large galaxies often dominate clusters of smaller ones, a hierarchy of scales where giants feed on dwarfs, merging and growing over time. The collisions of galaxies are among the most breathtaking events in the universe. Though stars rarely collide directly, the gravitational interactions between galaxies transform their shapes in dramatic ways. Spirals can be stretched into long arcs, twisted into bridges, or fused into ellipticals. Gas clouds crash together, igniting bursts of star formation so intense that astronomers call them starbursts. In these brief periods, a galaxy can create new stars at rates hundreds of times faster than normal, lighting up the universe with a surge of brilliance. Eventually, the frenzy subsides, and the merged galaxy settles into a new form, often larger and smoother, with the scars of its past preserved in faint shells or streams of stars. Such collisions are not rare exceptions but a natural part of galactic life. Our own Milky Way is on such a path. In 4 billion years, it will meet Andromeda, and the two spirals will entwine. From Earth, if any eyes remain to witness it, the night sky will fill with arcs of light, Andromeda growing larger until it dominates the heavens. Over time, the two galaxies will merge, forming a new elliptical, or perhaps a giant disk, its stars rearranged into new orbits, its black holes united in a final collision. Far from being an end, the event will be a transformation, the birth of a new galactic identity. The diversity of galaxies is more than a catalogue of forms. It is evidence of history written across the cosmos. Every warped arm, every faint stream of stars, every smooth ellipse is a record of encounters and transformations. Galaxies are shaped not only by their contents but by their neighbors, by their environment, and by the invisible scaffolding of dark matter that binds them. They are not static islands but dynamic, evolving structures, alive with the processes of creation and change. And as we trace their forms and their stories, we find ourselves drawn outward to an even larger perspective. Galaxies themselves, magnificent though they are, do not exist alone. They gather into clusters and superclusters, weaving into vast networks that stretch across billions of light years. To see this greater pattern is to glimpse the cosmic web itself, the grandest structure in existence. The largest galaxies are titans of light and gravity, sprawling systems whose scales defy the imagination. Consider IC 1101, one of the largest galaxies known. It lies in the Abell 2261 cluster and measures nearly 6 million light-years across. If our Milky Way were placed inside it, it would be little more than a glittering grain in a continent of stars. IC 1101 is not a graceful spiral, but a giant elliptical, its form smoothed by countless collisions and mergers. It contains hundreds of trillions of stars, each one a sun with its own story. Yet from afar, they blend into a soft golden glow. To contemplate such a leviathan is to realize that even galaxies, grand as they seem, are themselves but building blocks of something larger. And yet, some of the strangest galaxies are not the largest, but those that carry odd signatures of their past. Ring galaxies, for example, reveal the scars of collisions. A smaller galaxy passes through a spiral, setting off waves of star formation that spread outward in rings. To our eyes, they appear as glowing circles suspended in darkness, eerie and beautiful. Other anomalies include polar ring galaxies, with bands of stars and gas orbiting at right angles to the main body, and galaxies with double nuclei, where two cores orbit one another within the same halo of stars. These oddities remind us that galaxies are not static structures, but dynamic systems shaped by chance and circumstance. There are also faint dwarf galaxies, so dim that they are difficult to detect even with the most powerful telescopes. Some are little more than collections of a few thousand stars, barely held together by gravity, yet they are vital clues to the history of galaxy formation. They may be remnants of ancient collisions, survivors of a more chaotic era in the early universe, or companions slowly being consumed by their larger neighbors. Their very fragility speaks of a universe in motion, where even galaxies live and die. Astronomers have discovered galaxies with astonishing properties. Some seem to lack dark matter, defying expectations of how galaxies form and hold together. Others are dominated almost entirely by dark matter, with few stars to light them. Some galaxies shine with furious bursts of creation, while others have been quiescent for billions of years. The range is staggering, a cosmic menagerie that continues to expand as new instruments peer deeper into the night. With each discovery, our picture of galaxies grows richer and stranger, a reminder that the universe is more diverse than our imaginations can easily encompass. And yet, for all their diversity, galaxies do not float alone. They are bound together into clusters, hundreds or thousands of galaxies linked by gravity. These clusters themselves are woven into larger formations, superclusters that extend across hundreds of millions of light years. The galaxies we see are like lights in a grand tapestry, threads and knots in a structure of unimaginable scale. When astronomers map the distribution of galaxies across the sky, patterns emerge. Long filaments stretch for billions of light years, with galaxies strung along them like pearls. Between these filaments lie vast voids, regions almost empty, spanning hundreds of millions of light years. The galaxies, magnificent though they are merely the luminous traces of something greater, the cosmic web. In leaving behind the scale of single galaxies and even clusters, we step into the architecture of the entire universe. Galaxies are not isolated islands, but points in a vast network, connected by the gravity of unseen matter, shaped by forces both visible and invisible. To study galaxies is to stand at the edge of this greater structure, to see the first hints of the web that binds all things together. The journey that began with the measure of light years has now taken us to the brink of the grandest design of all. The universe is not random but patterned, not chaos but order written on the largest possible canvas. To follow that pattern, we must now move beyond galaxies and enter the cosmic web, where the true immensity of creation is revealed. If galaxies are islands of stars, then the cosmic web is the ocean that holds them, a vast structure stretching across the entire observable universe. It is not random, it is patterned, woven like threads of silk across billions of light years. The galaxies we see through telescopes are not scattered evenly but arranged in filaments, enormous strands that form the scaffolding of the cosmos. Between them lie immense voids, regions so empty that they dwarf even the largest galaxies. To map this web is to glimpse the architecture of creation itself. The cosmic web was first revealed in large sky surveys, where astronomers charted the positions of galaxies across wide regions of space. What emerged was not chaos, but order. Galaxies clustered into filaments and walls, leaving behind great bubbles of emptiness. These voids can span hundreds of millions of light years, nearly devoid of stars, while the filaments stretch like highways connecting clusters and superclusters. The largest of these structures, such as the Sloan Great Wall, extend more than 1 billion light years. The largest coherent structures ever observed. Gravity is the sculptor of this pattern. In the early universe, tiny fluctuations in density gave rise to regions slightly more massive than their surroundings. Over billions of years, gravity amplified these variations, pulling matter together into sheets and filaments. The densest knots became clusters of galaxies, while the spaces between grew emptier. What we see today is the frozen imprint of that process, the result of billions of years of growth, a cosmic web spun from the simplest of beginnings. This web is not only made of visible matter. In fact, the galaxies we see are only tracers, small points of light in a much larger structure of dark matter. Invisible to our eyes, dark matter exerts gravity, shaping the distribution of galaxies, guiding their formation, and holding clusters together. Without it, the web could not exist as we see it. The galaxies hang like lanterns on a scaffold of invisible threads, glowing markers of something deeper and hidden. The scale of the cosmic web is staggering. Imagine zooming outward from Earth, past the solar system, beyond the Milky Way, across the local group, and into the Virgo supercluster. Still, we are nowhere near the full extent. The web stretches beyond imagination, a pattern that repeats across scales so vast that our entire galaxy becomes a single node in a network spanning billions of light years. The distances are not merely numbers but realities. Space is so large that light takes billions of years to cross them, longer than the span of most galaxies themselves. And yet, within this immensity lies a kind of elegance. The web resembles the branching of trees, the networks of rivers, even the neurons in a brain. It is as though the universe itself has grown into a structure both immense and familiar. Echoing patterns we know from nature, scientists have compared the distribution of galaxies to the filaments of a spider's web or the tendrils of coral. It is a reminder that complexity can arise from simplicity, that the same physical laws shaping atoms can also sculpt the largest structures in existence. To walk the cosmic web in thought is to journey through emptiness and abundance alike. Filaments blaze with galaxies, clusters teeming with hundreds or thousands of suns. Then comes the sudden drop into voids, vast regions with only a few lonely galaxies scattered across them. These voids are not entirely empty, but compared to the richness of filaments, they are deserts of space, dark and silent. The contrast is stark. The web is a tapestry of light and dark, a cosmic yin and yang that stretches across the observable universe. As we map these structures, we find still greater mysteries. Some regions of the web seem to pull on galaxies with strange power, as though anchored by something unseen. One such region, known as the Great Attractor, tugs entire clusters toward it, with gravity so strong that even our own local group is drawn into its flow. What lies there is partly obscured, hidden behind the dust of the Milky Way, but its influence is undeniable. It is a reminder that the web is not merely a static pattern, but a living structure, still evolving, still drawing matter into its knots. The cosmic web is the skeleton of the universe, the grand framework upon which everything else is built. To see it is to understand that galaxies are not isolated but connected, that we are part of a structure far larger than any star or world. And yet, the web itself raises questions. What holds it together? What drives its growth? The answer lies in forces both visible and invisible, in dark matter and in the even stranger influence of dark energy. To follow the threads of the web is to be led inevitably toward the mysteries of the unseen. The vastness of the cosmic web becomes even more striking when we pause to consider the voids. These regions, stretching hundreds of millions of light years across, are not empty in the absolute sense, but compared to the filaments, they are almost desolate. A few faint galaxies may drift within them, lonely wanderers adrift in seas of darkness. But for the most part, they are expanses of space where almost nothing has gathered. The contrast between these voids and the luminous filaments is sharp. It is as if the universe has grown into a pattern of highways and deserts, channels and hollows, each complementing the other. Superclusters rise where filaments meet. These are colossal structures made of thousands of galaxies bound together by gravity. The Virgo supercluster, of which our Milky Way is a part, is only one node in an even greater system called Laniakea, a structure spanning more than 500 million light-years. The name, drawn from the Hawaiian word for immense heaven, is fitting, for Laniakea is a realm so vast that it dwarfs everything we usually imagine when we think of scale. Within it, rivers of galaxies flow toward a common center, drawn by gravitational currents that shape their motion. And beyond Laniakea lie still more superclusters, each one another knot in the grand web. At the heart of these gravitational flows lies one of the great mysteries of modern astronomy, the Great Attractor. This region exerts such powerful pull that hundreds of thousands of galaxies, including our own, drift toward it. Yet it lies partly obscured behind the plane of the Milky Way, hidden by dust and stars. We know it only by its influence, by the way it alters the motions of galaxies across vast distances. What lies at its center is uncertain, though many suspect an enormous concentration of dark matter and galaxies, a gravitational well carved in the invisible. The Great Attractor is a reminder that the universe still holds secrets in plain sight, pulling on us even as we struggle to see it. The cosmic web is shaped not only by gravity, but by the unseen hand of dark matter. Without it, galaxies could not have formed where they did, nor would the web have taken its intricate shape. Dark matter provides the scaffolding, the invisible framework upon which the luminous structures are built. Though we cannot see it directly, its fingerprints are everywhere. Computer simulations that include dark matter recreate the web in astonishing detail, showing how invisible mass shepherds visible matter into filaments and clusters. In these models, the universe grows like frost on glass, branching and spreading, a frozen echo of the laws of physics played out on the grandest stage. Even more surprising is that the web itself is not static. It is still evolving. Galaxies continue to fall toward clusters, clusters merge into superclusters, and filaments grow as matter flows along them. Over billions of years, the web changes shape, just as a living organism might. Yet there is a limit to this growth. The expansion of the universe, driven by dark energy, is accelerating, pulling galaxies apart faster and faster. In time, the web may unravel, its filaments stretching until galaxies slip beyond each other's horizons, leaving behind only local clusters bound by their own gravity. The cosmic web is not eternal but transient, a stage in the history of the universe. The beauty of the cosmic web is that it connects the smallest and the largest. Tiny fluctuations in the early universe, smaller than an atom, grew over billions of years into filaments, billions of light years long. The physics that shaped electrons and protons also sculpted the grand architecture of the cosmos. To see the web is to see unity, a seamless connection between the microcosm and the macrocosm, between quantum fluctuations and galactic superclusters. It is a pattern that speaks of deep laws, of simplicity, giving rise to complexity, of the universe writing itself on every scale. The cosmic web is the stage, the skeleton, the framework, and yet, for all its grandeur, it raises questions we cannot ignore. What is the dark matter that holds it together? What is the dark energy that tears it apart? To step beyond the visible filaments and voids is to confront the invisible forces that shape everything. The next step in our journey leads us into those shadows, into the unseen that governs the fate of the cosmos itself. The largest known structures in the universe stretch the limits of what we can even call a thing. Among these is the Hercules Corona Borealis Great Wall, a colossal formation of galaxies spanning more than 10 billion light-years. To put this into perspective, that is nearly 1/4 the diameter of the observable universe itself. Structures like this challenge our understanding of how matter can be arranged on such scales. They are not galaxies, not clusters, but entire walls of galaxies, immense sheets, and filaments that define the very skeleton of the cosmos. When astronomers discovered them, they forced us to rethink whether the universe had limits to its structure, or whether the web could truly extend without bound. The cosmic web is traced not only by galaxies, but also by the thin gas that stretches between them. Recent observations have revealed that these filaments contain much of the universe's missing matter, faint clouds of hydrogen heated to millions of degrees. Though invisible to the naked eye, they glow faintly in ultraviolet and X-ray light, a hidden skeleton carrying the weight of the cosmos. The galaxies themselves are but jewels strung along these threads, tiny concentrations compared to the vast bridges of matter connecting them. In the deepest sense, the cosmic web is a map of gravity and time. It shows us how the universe grew from its earliest moments, how tiny fluctuations in the first fractions of a second blossomed into structures spanning billions of light years. It reveals how dark matter gathers, how visible matter follows, and how galaxies form at the intersections. It is the ultimate expression of simple laws playing out across unimaginable scales, proof that from the smallest seeds can grow the grandest trees. And yet, the web is incomplete without forces we cannot see. Dark matter provides the scaffolding, but it is not matter as we know it. It neither emits nor absorbs light, and its nature remains elusive. Then there is dark energy, a mysterious pressure that pushes the universe to expand ever faster, threatening to pull the web apart. Together, these unseen influences shape the fate of the cosmos more profoundly than anything visible. The luminous filaments and galaxies are only the surface of a deeper, hidden reality. The cosmic web is both breathtaking and humbling. It shows us that we are not merely residents of a galaxy, but nodes in a network beyond comprehension. The Milky Way, the Andromeda Galaxy, the Virgo supercluster, even the Great Attractor, all are strands in a tapestry whose full extent we may never grasp. To gaze upon it is to realize that the universe is not only vast but connected, a living structure where every star, every planet, and every atom belongs to a pattern far greater than itself. And so, our journey turns toward the unseen. For if the web is the visible skeleton of the universe, then the flesh and the forces that hold it together are invisible. What is this dark matter that builds the scaffolding? What is this dark energy that stretches it apart? These are the questions that lead us forward, into a chapter where the greatest mysteries of the cosmos await. The galaxies and filaments of the cosmic web shine brightly, but their brilliance is only a thin layer on the surface of a much deeper mystery. What we see is not all that exists. In fact, the matter that forms stars, planets, and people accounts for less than 1/5 of the total. The rest is hidden, unseen, yet undeniable, shaping the cosmos in silence. It is a reminder that the universe does not reveal itself fully to the eye, and that what is invisible can be more powerful than what is bright. Dark matter was the first of these unseen forces to reveal its presence. In the 1930s, astronomer Fritz Zwicky studied the Coma Cluster, a collection of galaxies bound together by gravity. He discovered that the galaxies moved so quickly that the visible matter could not account for their motions. There had to be more mass holding them together, something unseen. Decades later, Vera Rubin confirmed this mystery by studying the rotation of spiral galaxies. She found that stars in the outer regions moved just as fast as those near the center, defying Newton's laws if only visible matter was present. The conclusion was inescapable. An invisible substance, far more abundant than ordinary matter, was shaping galaxies from the inside out. Dark matter does not emit or absorb light. It passes through ordinary matter almost without interaction, making it nearly impossible to detect directly. Yet its gravitational influence is unmistakable. It holds galaxies together, binds clusters, and weaves the cosmic web. Without it, stars would drift apart, galaxies would unravel, and the universe as we know it would not exist. Roughly 85% of all matter in the universe is dark matter, a substance we cannot see but cannot deny. The search to identify what dark matter truly is has become one of the great quests of modern physics. Some theories suggest it is made of exotic particles that barely interact with normal atoms, such as WIMPs, weakly interacting massive particles. Others propose axions, particles so light and elusive that they slip through the cosmos unnoticed. Massive neutrinos, once thought massless, may play a role, though their known properties cannot explain all of the observations. Around the world, experiments in deep underground laboratories wait for rare collisions between dark matter and ordinary matter, hoping to catch even the faintest signal. So far, the silence endures, the mystery deepens, yet dark matter is only half of the hidden story. In the late 1990s, astronomers studying distant supernovae made a discovery that stunned the scientific world. Instead of slowing under gravity, the expansion of the universe was accelerating. Some unknown force was pushing galaxies apart, counteracting the pull of matter and speeding the growth of space. This force was named dark energy, and it makes up nearly 70% of the total energy of the universe. Its nature is even more obscure than that of dark matter. It may be a property of space itself, a kind of vacuum energy that fills every corner of existence, or it may be a new field, something not yet imagined. Whatever it is, it dominates the fate of the cosmos. Together, dark matter and dark energy define the universe we inhabit. Ordinary matter, the atoms of stars and planets, is only a trace, a small fraction of the total. We live in a universe where the visible is the minority and the invisible reigns. Our telescopes can map the glow of galaxies, but the true cosmos is sculpted by forces beyond sight. This realization is both humbling and exhilarating. It tells us that what we know is only the beginning, that vast realms of physics remain undiscovered, waiting for us to uncover their secrets. And so we move forward, guided by invisible hands. Dark matter holds the web together, unseen scaffolding for galaxies and clusters. Dark energy stretches the web apart, an unknown pressure accelerating expansion. Between them lies the balance of the cosmos, the contest that will decide its ultimate fate. To explore these mysteries is to confront the deepest questions of science. What is the universe made of? Why does it expand the way it does? And what will its destiny be? The evidence for dark matter grows clearer the more we look for it, even though we cannot see it directly. One of the most striking proofs comes from gravitational lensing, a phenomenon predicted by Einstein's theory of relativity. Gravity bends space, and light follows the curves. When light from a distant galaxy passes through a cluster on its way to us, the cluster's mass warps the light, distorting or even multiplying the image. By studying these distortions, astronomers can map the distribution of mass in the cluster. Time and again, they find that the visible matter stars and gas accounts for only a small fraction of the bending. The rest must be caused by something invisible, the unseen hand of dark matter. Even more dramatic is the bullet cluster. Two galaxy clusters that collided hundreds of millions of years ago. When the hot gas from each cluster smashed together, it slowed and piled up in the middle, glowing brightly in X-ray light. But gravitational lensing showed that most of the mass had passed straight through, hardly interacting at all. The visible matter lingered in the center, while the dark matter drifted outward, invisible but undeniable. The bullet cluster is a cosmic crime scene, a snapshot that reveals dark matter separating from ordinary matter, leaving a signature too clear to ignore. Computer simulations bring the picture into even sharper focus. When astronomers model the universe with only ordinary matter, the resulting structures look nothing like reality. Galaxies fail to form, clusters lack the right shapes, and the cosmic web never emerges. But when dark matter is added, the universe in the simulation comes alive. Filaments and voids appear, clusters form, and galaxies gather at the intersections exactly as we observe them. The match is so precise that it is impossible to dismiss. Dark matter is not a hypothesis born of wishful thinking, but a necessity written into the very structure of the cosmos. And yet, the question of what dark matter actually is remains unanswered. Experiments around the world search for it with patience and precision. Deep underground, shielded from cosmic rays, detectors wait for the faintest signal of a dark matter particle striking an atomic nucleus. Tanks filled with liquid xenon, crystals of germanium, and arrays of sensitive sensors stand ready, their silence stretching on, year after year. Particle accelerators like the Large Hadron Collider probe high energies, hoping to create or reveal dark matter in the collisions of protons. Each experiment carries the promise of discovery, but so far, the darkness remains intact. Despite this, scientists are not discouraged. The history of physics is filled with mysteries that lingered for generations before breakthroughs came. The atom, once invisible, became clear through experiments with electricity and radiation. Neutrinos, once only a ghostly idea, are now detected routinely in vast underground chambers. Dark matter may be elusive, but its influence is everywhere, and its secret will not remain forever hidden. At the same time, the mystery of dark energy looms larger. If dark matter binds the cosmos, dark energy tears it apart. Its discovery at the close of the 20th century was one of the most profound shocks in science. For decades, astronomers assumed that the expansion of the universe, set in motion by the Big Bang, would slow under the pull of gravity. Perhaps it would slow forever, perhaps collapse back into a big crunch. But when distant supernovae were measured, their light revealed the opposite. The universe was not slowing, it was accelerating. Galaxies were racing away faster and faster, driven by something no one had anticipated. The nature of dark energy is even more obscure than dark matter. It may be a property of space itself, what Einstein once called the cosmological constant. In this view, empty space is not truly empty, but has energy that exerts a repulsive force, stretching the universe. Or dark energy may be a dynamic field, something that evolves over time, changing the rate of expansion. Each possibility carries profound implications. If it is a constant, the expansion will continue steadily. If it is dynamic, the universe's fate may be stranger still, with acceleration that changes in ways we cannot yet predict. For now, astronomers measure and wait. By mapping galaxies across billions of light years, by studying the faint glow of the cosmic microwave background, by tracking the behavior of supernovae, they hope to learn how dark energy has changed over time. The answer may reveal not only what the universe is doing now, but what it will do in the future. The balance between dark matter and dark energy will decide the ultimate destiny of everything we know. The cosmos has shown us its skeleton, the filaments and voids of the web. Now it has shown us the invisible forces that shape it, dark matter holding it together and dark energy pulling it apart. Between these two lies the struggle that defines the universe, the hidden battle between gravity and expansion. And as we contemplate these forces, unseen yet all-powerful, we turn to a different kind of wonder. The worlds that form within this vast stage, the planets that circle stars, each one a potential cradle of life. Dark matter and dark energy are the twin mysteries of the cosmos. And though we cannot yet see them directly, we continue to design new ways to probe their secrets. The search is as relentless as it is inventive. Physicists bury detectors deep beneath mountains, where Earth itself shields them from cosmic rays, leaving only the faint hope of a collision with a passing dark matter particle. In some experiments, tanks of liquid xenon wait in silence, every photon of light that flickers within them carefully measured for signs of the invisible. Others use crystals chilled to near absolute zero, where even the smallest vibration could betray a particle brushing against an atom. Each experiment is a patient vigil, a listening for whispers from a substance that has remained silent for billions of years. Astronomers also turn to the heavens for clues. Gravitational lensing provides maps of dark matter, tracing its hidden scaffolding through the way it bends light. The motions of galaxies in clusters reveal its presence, unseen but heavy. The cosmic microwave background, that faint afterglow of the Big Bang, carries imprints of how dark matter shaped the early universe. Every piece of evidence points to its dominance, and yet, its true nature continues to elude us. It may be a new kind of particle, or it may be something stranger still, something not yet imagined. Dark energy is even harder to pin down. Unlike dark matter, it does not gather or cluster, but acts uniformly, everywhere, all at once. Its discovery came not from laboratory experiments, but from the cosmos itself. Supernovae revealed its presence, but today, vast surveys of galaxies provide more detail. By charting how galaxies cluster across billions of light years, scientists measure how the expansion of the universe has changed over time. Projects such as the Dark Energy Survey and the Euclid mission seek to map the sky with unprecedented precision, searching for patterns that might distinguish whether dark energy is constant or dynamic. The answer could reshape not only cosmology, but physics itself. Some physicists wonder whether dark energy is truly a new force, or simply a reflection of our incomplete understanding of gravity. Einstein's general relativity has stood the test of a century. But perhaps it is not the full story. Perhaps on cosmic scales, gravity behaves differently than we expect, mimicking the effect of a repulsive energy. If so, then what we call dark energy may be a signpost pointing toward a deeper theory of space and time. The same possibility lingers with dark matter. Could the evidence be explained by new laws of gravity rather than new particles? For now, the balance of evidence favors their existence. But the debate keeps science alive, pushing us to test every assumption. The future holds hope for answers. The James Webb Space Telescope peers deeper into cosmic history, tracing the growth of the earliest galaxies and the imprint of dark matter upon them. Gravitational wave observatories may one day sense ripples caused by structures shaped in part by dark energy. Particle physics may reveal candidates for dark matter in accelerators or detectors. Each new instrument is a window, and each window brings us closer to lifting the veil. Yet perhaps the most profound truth is already clear. Ordinary matter, the stuff of stars and life, is a minority. We are built from atoms, but atoms form less than 5% of the cosmos. The rest is invisible. Dark matter and dark energy shaping the grand design. The universe is not what it seems. What we see is but the surface of a far greater reality. This knowledge is humbling, but it is also liberating. It reminds us that mystery is not failure, but invitation. The fact that most of the universe is invisible tells us that discovery is still alive, that the cosmos is not exhausted, that wonder remains. As we continue to explore, we carry with us the knowledge that even what we cannot see binds us, guides us, and determines our fate. And so, we turn from the invisible to the tangible, from the scaffolding of the cosmos to the worlds that orbit distant stars. For if dark matter and dark energy tell us what the universe is made of, then exoplanets and alien worlds tell us what the universe can become. Beyond the invisible forces lie strange new Earths, hot Jupiters, and frozen wanderers. Planets that may carry the promise of life or the silence of barren stone. Having explored the unseen, our journey now moves toward the worlds that await us among the stars. The night sky has always stirred the question, are we alone? For most of history, the stars seemed eternal and unreachable, and the planets of our solar system the only possible abodes of worlds. Yet in the past 3 decades, astronomy has answered with a revelation that has changed everything. Planets are not rare, they are everywhere. The Milky Way alone may hold trillions of them, orbiting nearly every star we see. Beyond the constellations, beyond the spirals of galaxies, lies a universe of alien worlds waiting to be discovered. The first confirmed exoplanets were detected in the 1990s. Astronomers found them not around a sun-like star, but around a pulsar, a collapsed remnant of a dead star. The discovery was astonishing. Even in such hostile environments, planets could survive. Soon after, techniques improved, and planets began to appear around ordinary stars. The breakthrough came with the Kepler mission, launched in 2009. By watching a patch of sky for years, Kepler measured the faint dips in starlight that occurred when planets crossed in front of their suns. The results were staggering. Thousands of planets were revealed, in every shape and size, orbiting stars of every kind. Kepler taught us that planetary systems are the rule, not the exception. For every star in the galaxy, there are likely worlds circling it. Some are giants larger than Jupiter, some smaller than Earth, and many defy expectations entirely. There are hot Jupiters, gas giants that orbit so close to their stars that their atmospheres boil away. There are super-Earths, rocky planets larger than our own, with the potential to host oceans and atmospheres unlike anything we know. There are mini-Neptunes, strange hybrids with thick atmospheres and rocky cores. And there are rogue planets, wandering alone through interstellar space, ejected from their systems, drifting forever in darkness. One of the most remarkable finds is the TRAPPIST-1 system, a red dwarf star orbited by 7 Earth-sized planets. 3 of them lie within the star's habitable zone, where liquid water might exist. Their orbits are so close together that standing on one world, you could see the others looming in the sky. Larger than the moon appears from Earth. It is a vision both alien and familiar, a reminder that planetary systems can be more diverse than anything we imagined. Exoplanets challenge our understanding of what is possible. Some worlds have days that last only a few hours, their years shorter than a week. Others take thousands of years to circle their stars. Some are tidally locked, with one side forever scorched by light, and the other frozen in eternal night. Some orbit double stars, with two suns rising and setting in strange dances of light. Others orbit stars so unstable that their skies would blaze with constant storms of radiation. And yet, among this diversity, some planets may be like home. Within the habitable zones of stars, where water can remain liquid, Earth-like conditions may arise. Kepler has shown us that such planets are common. Perhaps one, in every 5 sun-like stars, hosts a world in the right zone for life. That means, in our galaxy alone, there could be billions of potentially habitable worlds. Not all will be Earth-like. Some may be water worlds, covered in endless oceans. Others may be desert planets, dry and harsh but still alive. Life may thrive in forms we cannot yet imagine. The search for exoplanets is not only about numbers, but about possibility. The James Webb Space Telescope now studies the atmospheres of these distant worlds, looking for signs of water, methane, carbon dioxide, and even oxygen. Though the distances are immense, the tools are sensitive enough to begin probing their skies, searching for biosignatures, hints that life may exist elsewhere. Each discovery brings us closer to an answer to the oldest question: are we alone in the universe? Planets are not rare. They are everywhere, in endless forms, scattered across the galaxy. To realize this is to feel both small and immense. Small, because Earth is one world among billions. Immense, because life here may be part of a greater cosmic story, one written across the stars. The exoplanets remind us that we are not confined to one solar system, that the universe is richer than our ancestors could ever have dreamed. And yet, the strangest worlds may not be light years away. They may lie within our own solar system, orbiting the same sun, hiding oceans beneath ice or storms within clouds. Having looked outward to alien planets, we now turn inward, to the oddities of our own backyard, where moons and giants hold mysteries no less profound than those of distant stars. The zoo of exoplanets grows stranger the more we search. Among the most surprising discoveries are the hot Jupiters, giant planets that circle their stars at distances closer than Mercury is to the Sunday. Some of them orbit in only a few days, whipped around by gravity so tightly that their atmospheres swell and stream away into space. These worlds are unlikely to harbor life, yet they revealed something crucial. Planetary systems are far more diverse than our own. For centuries, we assumed other systems would resemble ours, with small rocky planets near the star and giants farther away. Hot Jupiters shattered that assumption, teaching us to expect the unexpected. Then there are the super-Earths, planets larger than our world but smaller than Neptune. They are among the most common types of planets in the galaxy, yet our solar system has none. Some may be rocky with thick atmospheres, others may be water worlds with global oceans, and still others may be mini-Neptunes with layers of hydrogen and helium cloaking a solid core. The very fact that such planets are so frequent, and yet absent from our neighborhood, reminds us that our solar system is not the rule, but the exception. Equally fascinating are rogue planets, worlds that have been flung out of their systems by gravitational interactions. Imagine a planet adrift in interstellar space, traveling endlessly without a sun, its skies forever dark. Some may still harbor warmth in their cores, enough to keep subsurface oceans liquid beneath layers of ice. Life on such worlds would be alien in the truest sense, surviving without sunlight, thriving in deep oceans warmed only by geothermal heat. Billions of these wanderers may exist in the Milky Way alone, silent nomads drifting between the stars. The idea of habitability has grown richer with these discoveries. We used to think of the habitable zone, the distance from a star where liquid water can exist, as a narrow band. But now we know that conditions for life may be found in unexpected places. Tidally locked planets, with one side in endless day and the other in endless night, may still harbor habitable twilight zones. Moons of giant planets, if large enough, may sustain atmospheres and oceans warmed by both their star and the tidal heating from their parent world. Even rogue planets may hide warm havens beneath their frozen shells. Life, it seems, may find a way in environments far more diverse than Earth's. The search has only just begun. Telescopes like James Webb are capable of analyzing exoplanet atmospheres when they pass in front of their stars. In the starlight filtering through, scientists can detect the fingerprints of molecules, water vapor, methane, carbon dioxide, even oxygen. Each detection is a step closer to finding worlds that might resemble home. The day may come when we see the unmistakable signs of life in the atmosphere of a distant planet, a discovery that would change our place in the cosmos forever. Exoplanets remind us of possibility. They tell us that Earth is not unique, that other worlds circle other suns, and that life may be only one of countless experiments across the galaxy. To look up at the stars is to know that each one may have its own family of planets, its own stories of oceans and deserts, mountains and skies. In those stories may lie companions, waiting across the light years, bound to us by the shared fabric of existence. And yet, even as we marvel at these alien worlds, we must remember that strange and wondrous planets exist much closer. Within our own solar system, familiar to us yet still mysterious, lie moons with seas of methane, ice worlds with oceans beneath their crusts, and storms that rage for centuries. To journey from the exoplanets back to our home system is not to step away from mystery, but to discover that the wonders of space begin right here, in our own cosmic backyard. The search for alien worlds is not just a catalogue of numbers, but a quest for meaning. For every super-Earth, hot Jupiter, or rogue wanderer, we are asking a deeper question. Which of these worlds could harbour life? The concept of the habitable zone, that region around a star where liquid water can exist, guides much of our search. Around stars smaller and cooler than the Sun, the habitable zone lies close in, so near that a planet might complete an orbit in only a few days. Around hotter, larger stars, the zone stretches farther out, placing potential Earth-like worlds at wider orbits. But habitability is not just a matter of distance. A planet's atmosphere can thicken or thin, trapping heat or bleeding it away. A world at the right distance may still freeze if its air is too thin, or boil if its atmosphere is too dense. Oceans, continents, magnetic fields, and even the presence of moons may all affect the balance. Habitability is a delicate equation, and nature experiments with it endlessly across the galaxy. The lesson is clear. While the habitable zone gives us a starting point, life may flourish in conditions far outside what we expect. Already, our instruments are beginning to sniff the skies of distant planets. When an exoplanet passes in front of its star, a fraction of starlight filters through its atmosphere. That light carries signatures of molecules: oxygen, water vapor, carbon dioxide, methane. With telescopes like James Webb, we can begin to detect those signatures, searching for chemical patterns that may indicate life. This search for biosignatures is still in its infancy, but even the first results remind us that the day may come when we identify a planet not only with the right size and orbit, but with the right chemistry for life. The possibilities stretch further still. Imagine a super-Earth with oceans 100 kilometers deep, covering its surface in endless blue. Imagine a desert planet with thin air but hardy life clinging to its shaded canyons. Imagine a world warmed not by a star but by tidal heating, its oceans kept liquid beneath an icy crust by the pull of a giant planet. These are not fantasies but logical outcomes of physics and chemistry, already glimpsed in data and theory. Life, if it is flexible, may find homes in places stranger than any Earth-like paradise. The discovery of exoplanets is more than science. It is a philosophical shift. For millennia, humans believed Earth to be unique, the center of creation. Then we learned that Earth is one planet among several, circling an ordinary star. Then we learned that the Sun is one among hundreds of billions in the Milky Way. Now we see that nearly every star has planets, that worlds are as common as grains of sand. Earth is not alone. It is one of countless shores on the ocean of the cosmos. And yet, the discovery does not diminish us. It deepens us. It tells us that the conditions for life are not rare, that the story of Earth may not be singular. Somewhere among the exoplanets, perhaps life stirs, perhaps civilizations rise, perhaps eyes look up at their skies and wonder, as we do. To know this is to feel both humbled and connected, to see ourselves not as the center, but as part of a vast family of worlds. The exoplanet revolution has shown us what lies beyond, but there are still marvels waiting closer to home. Our own solar system, familiar yet strange, holds oddities no less fascinating than alien worlds. Moons with seas of methane, icy shells hiding oceans, storms that rage for centuries, all within reach of our spacecraft. As we leave behind the exoplanets, we turn inward, to the wonders of our own backyard, where mystery is never far from home. The search for alien worlds has carried us across light years, but some of the strangest and most wondrous worlds lie much closer, circling our own Sunday. The solar system, far from being a set of familiar spheres, is a menagerie of extremes. Its moons and planets hold methane seas, volcanic hellscapes, hidden oceans, and storms that rage for centuries. Though we often look outward to distant stars, we need only explore our own neighborhood to encounter landscapes as alien as any exoplanet. Consider Titan, Saturn's largest moon. It is larger than Mercury, with a thick atmosphere rich in nitrogen and methane. On its surface, rivers and lakes glisten, not with water, but with liquid methane and ethane. Rain falls from orange clouds, carving channels into the icy crust, filling seas larger than the Great Lakes combined. It is the only other world in the solar system where stable liquids exist on the surface, a hydrological cycle of hydrocarbons mirroring the water cycle of Earth. To stand on Titan would be to see mountains of ice and valleys filled with alien seas, a mirror of home twisted into something strange and beautiful. Then there is Io, the innermost of Jupiter's large moons. Io is the most volcanically active world in the solar system. Its surface is scarred by hundreds of volcanoes, some blasting plumes of sulfur dozens of kilometers into space. The entire moon is constantly reshaped by this volcanic fury, its landscape a churning, molten canvas of reds, yellows, and blacks. The cause is tidal heating. As Io orbits Jupiter, it is pulled and stretched by the planet's immense gravity and the competing tugs of neighboring moons. This endless kneading generates heat enough to melt rock, driving eruptions more violent than anything on Earth. Io is a world of fire, born not of sunlight but of gravity. Europa, another of Jupiter's moons, presents a very different face. Its surface is a shell of ice, cracked and ridged, hiding beneath it a global ocean of liquid water. Evidence suggests this ocean may contain more water than all of Earth's oceans combined. The cracks and geysers that vent into space hint at warmth below, perhaps driven by the same tidal heating that powers Io. In that hidden ocean, shielded from radiation and lit only by chemical reactions at hydrothermal vents, life could exist. If we ever find extraterrestrial life, Europa may be one of the first places it appears, not in the light of a star, but in the dark waters of an alien sea. These moons remind us that habitability is not limited to planets or to warm, sunlit zones. Life may find a home in methane seas, volcanic depths, or oceans beneath ice. Our solar system, familiar in the night sky, is already proof of the diversity of worlds. Each moon, each planet, each oddity is an experiment, a unique expression of the laws of physics and chemistry. And the list does not end with Titan, Io, and Europa. Further out, Neptune howls with supersonic winds. Saturn swirls with a hexagon-shaped storm at its pole, and the icy Kuiper belt hides dwarf planets with frozen hearts. The solar system is a gallery of wonders, each object a world, each world a story. To explore them is to see that strangeness is not distant but near, that the frontier of discovery begins with our own sun and its family of worlds. Neptune, the farthest major planet from the sun, is a world of deep blue, a frozen giant cloaked in storms of unimaginable force. Despite receiving little sunlight, its atmosphere rages with winds faster than sound, reaching nearly 2,000 kilometers per hour. These supersonic gales sweep through methane clouds, driving storms larger than Earth itself. One such storm, the Great Dark Spot, was discovered in the late 20th century, a vast vortex like Jupiter's Great Red Spot, but even darker and stranger. Though that storm has since disappeared, others have arisen, shifting and evolving in ways that reveal Neptune as a dynamic, restless world. To imagine standing in those winds is to imagine a force no human could endure. A planet that defies its distance from the Sun by roaring with unseen energy. Saturn, by contrast, is often celebrated for its majestic rings, but at its north pole lies an enigma, unlike anything else in the solar system. There, a storm shaped like a perfect hexagon whirls endlessly, a six-sided pattern etched into the clouds by the planet's turbulent atmosphere. The hexagon spans more than 30,000 kilometers across, larger than Earth itself, and has persisted for decades, perhaps centuries. Its shape is thought to be the result of standing waves in Saturn's atmosphere, a resonance that locks storms into a geometric dance. To look down upon it is to see order within chaos, a cosmic pattern drawn on the canvas of a gas giant. Beyond the planets and their moons lies the Kuiper Belt, a vast region of icy bodies orbiting beyond Neptune. Here dwell dwarf planets like Pluto, Eris, Haumea, and Makmak, each with their own peculiarities. Pluto, once considered the ninth planet, revealed itself through the New Horizons mission as a world of breathtaking complexity. Mountains of water, ice, plains of nitrogen glaciers, and a thin atmosphere that frosts and sublimates with the seasons. Its surface is marked by a heart-shaped plain, a symbol etched in ice that captured the imagination of Earth when first seen. Eris is even larger than Pluto, a frozen world that sparked the debate leading to Pluto's reclassification. Haumea spins so rapidly that it is stretched into an ellipsoid, flanked by a pair of moons. Makemake, reddish and distant, carries the secrets of the outer solar system in its icy shell. Still farther lies the Oort cloud, a hypothetical sphere of icy bodies surrounding the solar system at distances so vast that a single orbit could take millions of years. The comets that occasionally blaze into the inner solar system are believed to come from this distant reservoir, stirred from their slumber by passing stars or galactic tides. If the Kuiper Belt is our solar system's backyard, the Oort cloud is its outer wall, the frontier where the sun's influence gives way to interstellar space. Each of these places, from Neptune's storms to Saturn's hexagon, from Pluto's icy plains to the unseen Oort cloud, adds to the strangeness of our neighborhood. The solar system is not a collection of familiar orbs, but a menagerie of worlds, as alien as any we might find around distant stars. To explore them is to see the creativity of nature, to realize that even within a single system, the diversity of worlds is endless. The wonders of the solar system remind us that the universe need not be distant to be extraordinary. The frontier begins here, with the planets and moons circling our sun, with the belts and clouds that stretch into interstellar space. Yet beyond this backyard, beyond even the Oort cloud, lies the ultimate mystery, the fate of the universe itself. The further we travel outward, the stranger and more mysterious our solar system becomes. Beyond Neptune and the Kuiper Belt lies a frontier that remains mostly theoretical, yet profoundly important: the Oort cloud. This vast sphere of icy bodies is thought to encircle the solar system at distances so immense that a single orbit could take millions of years to complete. The Oort cloud may stretch halfway to the nearest stars, a distant halo of frozen remnants left over from the birth of the planets. We cannot see it directly, but we see its messengers. Long-period comets, those that streak across the sky once in a civilization's lifetime, are believed to come from this realm, disturbed from their slumber by the passage of stars or the pull of the galaxy itself. The Kuiper Belt, closer but still remote, is already filled with surprises. Pluto, once thought to be a frozen rock adrift in darkness, turned out to be a world of dazzling complexity. The New Horizons spacecraft revealed mountains of water ice as hard as stone, flowing plains of nitrogen glaciers, and a thin atmosphere that rises and falls with the seasons. Its heart-shaped plain, Tombo Regio, captured the imagination of Earth when first seen, a symbol carved in ice more than 1,000 kilometers across. Beyond Pluto lies Eris, nearly the same size but even farther away, a discovery that forced astronomers to rethink the definition of a planet. Haumea spins so rapidly that it has been stretched into a rugby ball shape, its surface gleaming with crystals of water ice. Makemake glows reddish in the darkness, another icy dwarf with its own story to tell. Each of these worlds, though small compared to the giants, carries secrets about the early solar system, fossils of its creation. Between these icy realms and the planets we know best are countless smaller oddities. Asteroids tumbling in eccentric orbits, centaurs crossing paths with the giants, comets blazing as they dive toward the Sunday. Even within the inner solar system, strangeness abounds. Mercury, locked in a slow spin, scorched on one side and frozen on the other. Venus, shrouded in clouds of carbon dioxide, its surface hot enough to melt lead. Mars, dry and cold today, yet scarred by rivers and lakes that once flowed across its surface. Each world is a puzzle, a reminder that familiarity should not be mistaken for simplicity. The solar system is our home, yet it is also a frontier as alien as any exoplanet. Titan's seas of methane, Io's volcanic infernos, Europa's hidden ocean, Neptune's supersonic winds, Saturn's hexagon storm, Pluto's icy heart. The distant comets of the Oort cloud, each is a chapter in the story of worlds. They remind us that strangeness does not begin beyond the stars, but within reach of our own spacecraft. To explore them is to see how diverse creation can be, even under the same Sunday. And as we leave behind our solar system, we carry with us the knowledge that every oddity is also a clue. These worlds tell us how planets form, how systems evolve, and how life might arise. They prepare us for what we may find among the exoplanets. For the alien is not truly foreign once we see its reflection at home. Yet even these marvels belong to a universe that is changing. The solar system is a small part of a cosmos that has its own story, its own beginning, and its own end. The planets and moons will endure for billions of years, but the universe itself faces a fate written in the balance of matter and energy. To move forward is to ask the final question: what is the destiny of all things? Every star, every planet, every galaxy is a temporary light in the long unfolding story of the cosmos. To ask about the fate of the universe is to ask not only about what will happen to the stars above, but also about the destiny of time itself. The answers we glimpse are sobering, yet they also carry a strange beauty. They remind us that creation and destruction are not opposites, but parts of the same whole, and that even endings are woven into the fabric of existence. The story begins close to home, with the fate of our own Sunday. For billions of years, it has burned steadily, fusing hydrogen into helium in its core, shining with the light that sustains life on Earth. But its fuel is finite. In about 5 billion years, the sun will begin to change. Its core will contract, its outer layers will swell, and it will become a red giant. Its diameter will grow until it engulfs Mercury and Venus, and Earth may follow, swallowed by fire. If Earth survives, it will be scorched, its oceans boiled away, its rocks molten under the heat. For a time, the sun will shine with a deep, ruddy glow, a swollen giant star nearing its end. Eventually, the sun will cast off its outer layers, creating a glowing shell of gas known as a planetary nebula. This nebula will expand into space, its colors drifting into the darkness, a final display of beauty as the star dies. What remains at the center will be a white dwarf, a dense core no larger than Earth but containing nearly half the mass of the original Sunday. It will shine faintly with residual heat, slowly cooling over trillions of years. Long after humanity and Earth are gone, the white dwarf will fade into darkness, becoming a black dwarf, a cold remnant adrift in space. The sun's story is not unique. Billions of stars across the galaxy will follow the same path, swelling into giants, shedding their layers, leaving behind white dwarfs. Others, more massive, will die more violently, exploding as supernovae and collapsing into neutron stars or black holes. The galaxy will grow darker over time, its stars fading, its brilliance dimming as fuel is consumed. The universe that was once ablaze with creation will grow quiet. But the fate of stars is only one part of the larger picture. The universe itself is expanding, galaxies rushing apart as space stretches between them. This expansion will shape the ultimate destiny of all things. If the expansion slows and reverses, the cosmos may collapse in a fiery big crunch. If it continues forever, stars will die out, galaxies will fade, and the universe will end in cold silence, a heat death where entropy reigns supreme. If dark energy grows stronger over time, expansion may accelerate until galaxies, stars, planets, and even atoms are torn apart in a big rip. Each possibility is written in the balance of forces we do not yet fully understand. To think of these fates is to feel the fragility of everything we know. Earth, the sun, the Milky Way, all are temporary. Yet there is also grandeur in this vision. The universe is not static but alive, a story with a beginning and an end. Its fate is not a tragedy but a testament to its nature, a reflection of the same laws that gave birth to stars, planets, and life. As we move deeper into the question of cosmic destiny, we will see how black holes evaporate, how protons may decay, how the very fabric of matter itself may unravel. The future stretches not for billions but for trillions upon trillions of years. A horizon so vast that our imaginations strain to follow. Yet it is in this horizon that the universe reveals its true scale. Not only in space, but in time, the future of the universe unfolds on scales so vast that human history seems but a flicker. After the last stars like our sun swell into red giants and fade into white dwarfs, the cosmos will enter an era of quiet decline. The bright, star-filled galaxies we see today will grow dimmer as stellar nurseries run dry, and the birth of new stars slows to a trickle. In time, the galaxies will shine only with long-lived red dwarfs, faint suns that burn slowly for trillions of years. Their glow will stretch across epochs unimaginable. But even they will eventually exhaust their fuel. Once the stars are gone, what remains are remnants, white dwarfs cooling into black dwarfs, neutron stars slowly fading in silence, and black holes waiting in darkness. The night sky of such a future would not be filled with constellations but with emptiness, punctuated only by the faint whispers of dying worlds. Galaxies themselves will continue to drift apart, carried by the expansion of space. As they separate, their light will redshift into invisibility, stretching until the cosmos grows dark to any observer. It will be a universe without stars, without galaxies, without light. The fate of matter itself may then be decided by processes even smaller and stranger than stars. Some theories suggest that protons, the building blocks of atoms, are not eternal. If they decay, then over spans of time 100 orders of magnitude longer than the current age of the universe, all matter will dissolve. Rocks, planets, stars, even white dwarfs will crumble into radiation, leaving behind only a sea of particles drifting in the dark. The cosmos would be reduced not only to silence, but to dust on the most fundamental level. Yet even black holes, the most enduring of cosmic remnants, are not forever. According to Stephen Hawking's theory, they slowly radiate energy, losing mass in the process. For the smallest black holes, this evaporation is rapid, but for supermassive black holes, it takes eons beyond comprehension. A black hole with the mass of the Sun might take 10 to the power of 67 years to vanish. A supermassive black hole with billions of solar masses could endure for 10 to the power of 100 years. But even these giants will eventually fade, ending their reign with a final burst of radiation, a last echo before the silence resumes. This scenario, where stars die, black holes evaporate, and matter itself decays, is called the heat death of the universe. It is a future where entropy, the measure of disorder, reaches its maximum. No energy gradients remain, no processes to fuel stars or life, only a thin, cold haze of particles spread across expanding space. It is not a fiery end, but a long fading, a slow and inexorable silence. But heat death is only one possibility. If dark energy changes over time, if it grows stronger instead of constant, the universe could meet a different fate. Galaxies would be torn apart, stars unbound from galaxies, planets from stars, atoms from nuclei. In this big rip, even space and time themselves could unravel, the expansion accelerating without limit until nothing remains. Such a scenario is speculative, but it reminds us that our knowledge of dark energy is still young. The true nature of this mysterious force could dictate a destiny stranger than we can yet imagine. On the other hand, if expansion one day slows and reverses, the universe could collapse in a big crunch. Galaxies would drift back together, stars and black holes merging, temperatures rising as space shrinks. Eventually, all matter and energy could converge into a singularity, an end that mirrors the beginning. Some theories even suggest that such a collapse could lead to a rebirth, a new Big Bang following the last, the universe cycling endlessly through creation and destruction. Each of these fates, the heat, death, the big rip, the big crunch, carries its own vision of the future, its own poetry of endings. We do not yet know which is true. The balance between dark matter, dark energy, and the expansion of space will decide. But all of them remind us of a profound truth. The universe is not static. It is a story still being written. And we are fortunate to witness even a single chapter of its vast arc. On the longest timescales, the universe becomes a theater of ghosts. The bright galaxies and stars we see today will be gone, leaving behind only the husks of matter. Black dwarfs, neutron stars, and black holes will populate the darkness, relics of a cosmos that once blazed with creation. But even these remnants are not immortal. If protons are unstable, then the very building blocks of matter will one day dissolve. Over timescales of 10 to the power of 34 years or more, rocks, planets, and even white dwarfs will disintegrate into showers of subatomic particles. The material of the universe will fade, not in fire, but in dissolution, a slow erosion into nothingness. If protons are stable, the black dwarfs and neutron stars may endure far longer, but entropy will still have the final word. Even the most enduring giants, black holes, are fated to disappear. Hawking radiation ensures that they are not eternal. Over unimaginable spans of time, they will evaporate, their mass leaking away as faint radiation. A stellar mass black hole might take 10 to the power of 67 years to vanish. A supermassive black hole, like the one at the center of the Milky Way, will endure for 10 to the power of 100 years. These numbers are so vast that they defy imagination. By the time the last black hole evaporates, every trace of galaxies, stars, and planets will be gone. The universe will be reduced to a thin, cold mist of photons and particles, spread across space, still expanding. This is the heat death in its final form, a universe where no process can create structure, no star can ignite, no life can endure. It is a cosmos that has reached maximum entropy, the long silence after the symphony has ended. Yet even here, there is a kind of awe. The universe is not destroyed in violence, but transformed into stillness. Its story is not one of sudden catastrophe, but of patient unfolding, a grand arc stretching across incomprehensible spans of time. And still, some speculate that even this may not be the end. Could the quantum fabric of reality itself give rise to new beginnings? Could fluctuations in the void spark new universes, each with its own laws, its own stars and galaxies, its own stories of creation and decay? If so, then our universe may be only one note in an endless chorus, a cycle of birth and death on scales even larger than what we now conceive. The fate of the universe is a mirror. It shows us how small we are in time and space. Yet it also shows us that we are part of this immense story. We live in a moment between the beginning and the end, a fragile window where stars shine and life can exist. To contemplate the universe's destiny is not despair, but perspective. It reminds us that meaning is not found in eternity, but in the finite moment, in the fact that against all odds, we are here to wonder at the cosmos at all. And so, having followed the story from the birth of stars to the death of the universe, we turn at last to the question of humanity itself. In this vast and ancient cosmos, what is our place? What does it mean to be small, yet aware, to be temporary, yet capable of wonder? To close this journey, we must step from the stars, back to ourselves, and ask what it means to live among them. When Voyager 1 turned its camera back toward Earth in 1990, it captured an image that has since become one of the most profound reflections on our existence. From a distance of 6 billion kilometers, Earth appeared as a pale blue dot, a single pixel suspended in a shaft of scattered sunlight. Carl Sagan, reflecting on this image, reminded us that all of human history, every king and peasant, every saint and sinner, every civilization and culture played out on that mote of dust suspended in a sunbeam. To see Earth so small against the backdrop of the cosmos is to realize that our home is both fragile and precious, a world adrift in immensity. Yet we are not bound only to gaze. In the 20th century, humanity began to reach outward, taking its first tentative steps beyond Earth. Yuri Gagarin's orbit in 1961, Neil Armstrong's first steps on the Moon in 1969, the robotic explorers that wandered across Mars and sailed beyond the planets. All were milestones in a journey that is still unfolding. Each mission carried not only instruments and experiments, but also a message that life on Earth, small as it seems, is capable of touching the stars. The Voyager spacecraft themselves are now messengers in the truest sense, carrying golden records etched with the sounds and images of Earth. They drift in interstellar space, silent emissaries that may one day be found by distant beings, or perhaps by no one at all. Whether or not they are ever discovered is almost irrelevant. What matters is that we, a species born on a single planet, had the imagination to send a greeting into the dark. More recently, the James Webb Space Telescope has shown us the universe in detail never before possible. Its infrared eyes peer into the earliest galaxies, revealing how the first stars ignited and how the cosmic web took shape. It studies exoplanet atmospheres, searching for signs of habitability, perhaps even hints of life. With every image it sends back, we are reminded that exploration is not only about rockets and astronauts, but also about vision, about the capacity to see farther and think bigger than ever before. Space exploration is not a luxury, nor merely a scientific endeavor. It is survival. The Earth will not remain habitable forever. Asteroids threaten, climate changes, the sun itself will one day swell and consume the inner planets. If life is to endure, it must spread. To journey outward is not only to satisfy curiosity, but to safeguard the flame of consciousness. Each spacecraft, each telescope, each rover is a step in the long road toward a future where humanity, or whatever we become, is not confined to one fragile world. Our place among the stars is not guaranteed, but it is possible. We are creatures of Earth, yet we are also children of the cosmos, made of elements forged in ancient stars. To know this is to realize that space is not foreign, but familiar. Not distant, but kin. The hydrogen in our bodies was born at the dawn of time. The carbon in our cells in the hearts of stars. The iron in our blood in supernovae. We do not merely live in the universe, we are of it. As we look forward, the pale blue dot reminds us to be humble, to cherish the world that birthed us. But it also reminds us to be bold, to see that the stars are not unreachable, but awaiting us. The story of the universe is vast, stretching across billions of years and trillions of worlds. Our story is young, only beginning. To ask what it means to be human among the stars is to ask what role we will play in the cosmos, what legacy we will leave in the great unfolding of time. Humanity's journey into space has unfolded step by step, each milestone a small triumph against gravity and time. After the first orbits of Earth, the Apollo program carried us farther than we had ever gone before. In 1969, Neil Armstrong and Buzz Aldrin set foot on the Moon, their footprints still preserved in the dust. For a brief moment, humanity was not confined to one world. The Apollo missions ended in 1972, but the vision they sparked has never faded. The Moon remains both a symbol and a destination, a reminder that we can leave Earth when we choose. In the decades that followed, human exploration turned inward, focusing not on new frontiers, but on building a presence in orbit. The International Space Station became a foothold in the sky, a laboratory circling Earth every 90 minutes. Astronauts from across the world have lived and worked there for more than 2 decades, studying how life adapts to microgravity, testing technologies, and showing what cooperation across nations can achieve. Though only 400 kilometers above Earth, the station represents something larger: humanity, learning to live beyond the surface of its home. Robotic explorers pushed the frontier outward. Mars became a land of machines, its red deserts roamed by rovers like Spirit, Opportunity, Curiosity, and Perseverance. Each one has carried our eyes and instruments to a world once thought lifeless and barren, revealing ancient riverbeds, dried lakes, and minerals formed in water. These discoveries suggest that Mars may once have been habitable, raising the possibility that life could have arisen there. Other probes ventured to the outer planets. Galileo orbited Jupiter, Cassini unveiled the beauty of Saturn. New Horizons flew past Pluto and revealed a world more complex than anyone had guessed. These missions extend human presence, showing that exploration is not only about astronauts, but about our robotic companions sent across the dark. Now, new dreams rise. Plans are underway to return humans to the Moon, to build bases and use its resources as a stepping stone to Mars. Missions like Artemis aim to establish a sustained presence, turning what was once a fleeting achievement into a permanent frontier. Mars itself beckons, though the challenges are immense. Radiation, distance, isolation, and survival in a harsh environment make it the most daring goal yet. But the vision of humans walking on another planet is no longer science fiction. It is a plan, slow in coming, but growing in resolve. Beyond Mars lies the challenge of interstellar travel. The distances are staggering. Even the nearest star system, Alpha Centauri, is over 4 light-years away. With current technology, it would take tens of thousands of years to reach it. Yet concepts exist: nuclear fusion drives, antimatter propulsion, solar sails pushed by lasers that could, in theory, cut the journey to decades or centuries. Projects like Breakthrough Starshot envision fleets of tiny probes, propelled by beams of light, racing to nearby stars at a fraction of the speed of light. They would be small, no bigger than a smartphone, but they could carry cameras and sensors, becoming humanity's first emissaries to other suns. These milestones and visions remind us of what is possible. From the first steps on the Moon to the rovers on Mars, from telescopes that see to the dawn of time, to probes that sail beyond the solar system, humanity has already begun its ascent into the cosmos. The road ahead is long, but the direction is clear. We are learning not only how to reach the stars, but how to endure among them. The question remains, why? Why should we cross such distances, spend such effort, risk such dangers? The answer is more than survival. It is curiosity. It is wonder. It is the drive that has carried us from caves to cities, from coastlines to continents, from Earth to the Moon. To go outward is to be human, and beyond survival or discovery, there is inspiration. To see Earth as a pale blue dot, to look back from another world, is to understand ourselves in ways impossible from the ground. Exploration is not an escape from Earth, but a deeper connection to it. A way of seeing that the planet we call home is precious beyond measure. Humanity's journey into the cosmos is not only about machines and missions. It is also about meaning. To leave Earth is to ask what role we play in the universe and what legacy we wish to leave behind. The stars remind us that our existence is fragile, yet they also remind us that it is filled with possibility. Every spacecraft launched, every telescope pointed upward, is a statement that curiosity is stronger than fear, that wonder is as essential as breath. The story of exploration is as old as humanity itself. We crossed mountains, seas, and deserts, not because we had to, but because we were compelled to see what lay beyond the horizon. Space is the greatest horizon of all. To step beyond Earth is not to abandon it, but to honor it, to carry its story into a larger stage. When astronauts looked back from the Moon and saw Earth rising above the lunar surface, they saw not nations, not divisions, but a single world, delicate and unified. That perspective is the gift of space. To see ourselves as one, small, yet extraordinary. Exploration also holds the key to survival. The Earth is vulnerable. Asteroids cross its orbit. Climate shifts threaten its balance. The Sun itself has a finite life. To remain confined to one planet is to live at the mercy of chance. To spread outward is to safeguard the continuity of life. Perhaps humanity as we know it will not endure, but something born of Earth, whether human descendants, artificial intelligences, or life we cannot yet imagine, may one day sail among the stars. In this sense, space exploration is not only ambition but duty, the duty to ensure that consciousness does not vanish when one fragile world falters. And yet, survival is not the only measure. The universe is vast, and the odds of finding other intelligences remain uncertain. We may be alone, or we may be one among many. But whether or not companions exist, the act of searching is itself a triumph. To look outward is to affirm that life, in its brief spark, seeks to understand itself. The cosmos may not offer us answers. Every fact about space, from the scale of galaxies to the mystery of dark matter, is more than trivia. It is a reminder of connection. The atoms in our bodies were forged in stars. The light we see tonight may have traveled billions of years to reach us. The universe is not separate from us. It is us. To know this is to carry humility and wonder in equal measure. And so, as we close this journey, we return to the image of the pale blue dot. That tiny pixel is our home, our history, our future. But it is not all. Around it are stars, galaxies, and the cosmic web itself, stretching into the infinite. We are small, yet we are part of something vast. We are temporary, yet we are made of elements that endure across eternity. We are fragile, yet we are capable of thought, imagination, and dreams that span the stars. The final truth is simple, yet profound. Every fact about the cosmos is a reminder. We are small, yet we are part of something infinite.